Welcome to one of the most elegant and powerful ideas in computer science, asymptotic notation. When we analyze algorithms, we don't care if your computer runs at 3 gigahertz or 4 gigahertz. We care about the fundamental mathematical relationship between input size and running time. Today we'll discover how big O, theta, and omega let us capture the essence of algorithmic efficiency with breathtaking precision. Here's why this matters. Imagine you wrote a sorting algorithm that takes exactly 3n squared plus 5n plus 2 milliseconds. Your colleague writes one that takes 2n log n plus 100 milliseconds. Which is better? For small arrays, who knows? But as n grows to thousands or millions, that n's word term will absolutely dominate everything else. Asymptotic notation strips away the noise and reveals the truth. O n log n beats O n squared O every single time for large inputs. Let's start with big O, the superstar of asymptotic notation. Big O gives us an upper bound. When we say f of n is O of g at n, we're making a promise. F will never grow faster than g, at least not once n gets large enough. Think of it as a speed limit for functions. You might drive slower sometimes, but you'll never exceed that ceiling. The formal definition involves constants c and n0, but the intuition is simple. F stays below some multiple of g eventually. Look at this beautiful relationship. We have f of n equals 2n squared plus 3n in blue, and we're claiming it's O of n squared. To prove this, we need to find constants c and n0 such that f of n stays below c times n squared for all n greater than n0. With c equals 3 and n0 equals 5, you can see that 2n squared plus 3n never exceeds 3n once we're past n equals 5. That red line becomes our ceiling, and our function respectfully stays below it forever. Now meet big omega, the flip side of the coin. While big O says never faster than, big omega declares never slower than. It's a lower bound, a floor that your function will never break through. This is incredibly powerful for proving that certain problems are inherently difficult. When we prove that comparison-based sorting is omega of n log n, we're not just analyzing one algorithm, we're proving that any comparison-based sorting algorithm must take at least n log n comparisons in the worst case. And here's the crown jewel, theta notation. Theta is the Goldilocks of asymptotic bounds. Not too high, not too low, but just right. When f of n is theta of g at n, we're saying they grow at exactly the same rate. F is sandwiched between two multiples of g. It has both an upper bound and a lower bound in terms of g. This is the tightest, most precise characterization we can give. Merge sort isn't just O n log n, it's theta n log n, meaning it always takes that long, no matter what the input looks like. Now we enter the realm of strict inequalities with small o. This is big O's perfectionist cousin. While big O allows equality, n squared can be O n squared, small o demands strict inequality. When f of n is O g n, f grows strictly slower than g. The limit of f over g approaches 0. Think binary search versus linear search. Log n isn't just O of n, it's actually O n because the ratio log n over n shrinks towards 0. Binary search doesn't just have a linear upper bound, it's genuinely, provably faster than linear. Finally, we have small omega, the mirror image of small o. Just as small o means strictly slower, small omega means strictly faster. When f of n is omega of g at n, f will eventually dominate any multiple of g. No matter how large a constant you pick, f will eventually outgrow that constant times g. It's the mathematical way of saying f wins in the long run, period. This notation captures the idea that some functions are destined to grow faster than others, with no possibility of a tie. Let's put these notations to work analyzing real algorithms. Linear search is beautifully simple. Scan through the array element by element until you find your target. But here's what makes it fascinating from an asymptotic perspective. The same algorithm can have dramatically different bounds depending on the input. In the best case, you get lucky and find your target immediately. In the worst case, the target isn't there at all, and you check every single element. Watch what happens in the best case. One comparison, target found. This gives us big omega of 1, a constant lower bound. No matter how large your array gets, there's always a chance you'll get lucky and find the target immediately. This demonstrates the power of big omega notation. It captures the best possible performance, showing that linear search can sometimes be incredibly fast. But notice we don't say theta of 1, because the worst case is much different. Now see the worst case unfold. We check element after element, reaching the bitter end without finding our target. That's n comparisons total, big O of n. If your array has 1,000,000 elements and the target isn't there, you'll do 1,000,000 comparisons. No way around it. This linear growth in the worst case gives linear search its name and its fundamental limitation. For large datasets, this O(n) worst case can be painfully slow. Enter binary search, one of the most elegant examples of logarithmic complexity. The key insight is brilliant. If the array is sorted, you can eliminate half the possibilities with each comparison. Check the middle element. If it matches, you're done. If your target is smaller, ignore the right half. If your target is larger, ignore the left half. With each step, the problem size halves. This halving process can only happen log(2n) times before you're down to a single element. This is why logarithmic algorithms are so powerful. If you have a sorted array with 1,000,000,000 elements, that's 2-qt, binary search will find any element in at most 30 comparisons. 1,000,000,000 becomes 30, 1,000,000,000,000 becomes about 40. Compare this to linear search, which might need 1,000,000,000 comparisons in the worst case. The gap between O log n and On becomes astronomical as n grows. This is small o in action. Log n is O of n, because log n grows strictly slower than n. Now let's witness the quadratic tragedy of bubble sort. The algorithm is deceptively simple. Repeatedly scan through the array, swapping adjacent elements that are out of order. But look at what happens. We have nested loops. The outer loop runs n times, and for each iteration of the outer loop, the inner loop does roughly n comparisons. N times n gives us n squared. Even for a modest array of 1,000 elements, that's 1,000,000 operations in the worst case. See how quadratic complexity scales. It's brutal. When you double the input size, the running time quadruples. An array of 2,000 elements takes 4 times as long as 1,000 elements. This quadratic growth is why bubble sort is generally considered impractical for large datasets. The best case gives us hope. If the array is already sorted, and we add an optimization to detect this, bubble sort can run in O(n) time. But that worst case O of n squared is what matters for algorithmic analysis. Insertion sort tells a more nuanced story. Like bubble sort, it's O(n) squared in the worst case, but it's adaptive. Its performance depends heavily on how sorted the input already is. The algorithm builds the sorted region one element at a time, inserting each new element into its correct position. In the best case, when the array is already sorted, each element is already in the right place. Just n1 comparisons total. Linear time. Selection sort is the most predictable algorithm we'll see. It's theta of n squared always. Whether the input is sorted, reverse sorted, or random, selection sort always does exactly the same amount of work. It finds the minimum element, swaps it to the front, then finds the minimum of the remaining elements, and so on. Each pass requires scanning all remaining elements. This gives us n plus n minus 1 plus n plus plus 1 comparisons, which equals n plus 1 the bar 2. That's theta of n squared. Tight bounds. Now we enter the beautiful world of recursive algorithms. Recursion changes everything about asymptotic analysis. Instead of counting loops, we write recurrence relations that describe how the problem breaks down into smaller subproblems. The magic happens when we solve these recurrences to find closed-form expressions for the running time. Master theorem, substitution method, recursion trees, these are the tools that unlock the secrets of recursive complexity. Merge sort is the crown jewel of divide and conquer. The recurrence relation is T of n equals 2Tn 2n. We split the array in half, recursively sort both halves, then merge them back together in linear time. Look at this recursion tree. It has log n levels because we keep halving until we reach single elements. Each level does O(n) total work merging. Log n levels times O(n) work per level gives us the famous O(n) log n bound. Here's what makes merge sort extraordinary. It's theta of n log n in all cases. Best case, worst case, average case, it doesn't matter. The algorithm always divides the problem exactly in half and always merges in linear time. This consistency is both a strength and a weakness. You get predictable performance, but but you can't take advantage of already sorted input like insertion sort can. The tree always has the same shape. The work is always distributed the same way. Quicksort with perfect pivots is a thing of beauty. When the pivot always splits the array into two equal halves, we get the same recurrence as merge sort. Tia n equals 2t of n over 2 plus on. The tree has log n levels, each level does on partitioning work, and we end up with on log n. In the best and average cases, quicksort matches merge sort's performance. The difference is that quicksort sorts in place, using only O log n extra space for the recursion stack. But quicksort has a dark side, the dreaded worst case. When the pivot is always the smallest or largest element, one partition gets n1 elements while the other gets 0. This creates a degenerate tree that's essentially a linear chain. The recurrence becomes Tia n equals Tia n minus 1 plus on, which solves to on squared. Ironically, this often happens with already sorted input if you naively pick the first element as pivot. That's why modern quicksort implementations use randomized or median of 3 pivot selection. Now witness one of the most spectacular failures in algorithmic design, naive recursive Fibonacci. The recurrence Tia n equals Tia n minus 1 of Tia n minus 2 plus O1 looks innocent enough, but it hides an exponential explosion. Look at this recursion tree. It's computing the same subproblems over and over again. F of 3 gets computed multiple times, F of 2 gets computed even more, and F of 1 gets computed exponentially many times. The total running time is O phi n, where phi is the golden ratio, approximately 1.618. See how exponential growth explodes as n increases. For n equals 40, naive Fibonacci makes over a billion recursive calls. For n equals 50, it would take longer than the age of the universe to complete. This is why exponential algorithms are generally considered intractable. The beautiful irony is that Fibonacci can be computed in O(n) time with dynamic programming, or even O log n time with matrix exponentiation. The lesson: recursive structure alone doesn't determine complexity. Overlapping subproblems can turn polynomial problems into exponential nightmares. Tower of Hanoi presents a fascinating contrast: exponential time that's actually unavoidable. The problem requires moving a stack of n disks from one peg to another, with larger disks never placed on smaller ones. The optimal strategy generates the recurrence Tn equals 2Tn minus 1 plus 1. To move n disks, you must first move the top n1 disks off the largest disk, move the largest disk, then move those n1 disks back on top. This gives exactly 2 minus 1 moves. Now let's master the art of rigorous asymptotic proofs. Proving that f of n equals of gn isn't just about intuition, it requires finding specific constants c and n0 that witness the bound. Let's prove that 2n squared plus 3n plus 1 is on squared. We need to find c and n0 such that 2n squared plus 3n plus 1 cn squared for all n no n 0. This is where mathematical precision meets algorithmic insight. Watch this proof unfold step by step. We start with 2n squared plus 3n plus 1 and need to bound it above by cn squared. The key insight is to bound each term separately. For large n, we can say 3n squared and 1n squared. So 2n plus 3n plus 1 into 2n squared plus n equals 4n. This means we can choose c equals 4 and the inequality holds for all n squared 1. We've constructively proven the on squared bound. Proving big omega requires the opposite approach. We need a lower bound. To show 2n squared plus 3n plus 1 is ob of n squared, we need c and n0 such that cn squared lay 2n squared plus 3n plus 1 for all n n0. The dominant term 2n squared makes this straightforward. For any positive c2, we can choose n0 large enough that the inequality holds. In fact, c equals 1 and n equals 1 work perfectly, since 2n plus 3n plus 1 row 2n n squared for all n1. The theta proof brings it all together. Since we've proven both 2n plus 3n plus 1 and n quin plus 3n plus 1 equals sums of n quid, we can conclude that 2n plus 3n plus 1 equals n squared. The function is sandwiched between 1n squared and 4n for all n squared are 1. This is the beauty of theta notation. It captures the exact growth rate by providing both upper and lower bounds. We've proven that this polynomial grows at precisely the same rate as n squared. Small o proofs often use limits to capture the intuition of strictly slower growth. To prove n equals n squared, we compute the limit of n squared as n approaches infinity. This limit equals 1n, which approaches 0. Since the limit is 0, we've proven that n grows strictly slower than n squared. This limit-based approach is often more elegant than the epsilon delta definition, especially when dealing with logarithmic or polynomial functions. Proving recursive bounds requires different techniques. For merge sorts T(n) equals 2Tn plus On, we can use the recursion tree method. The tree has log n levels, each doing On work. Level 0 does Cn work, level 1 does 2n per tau equals Cn work, and so on. Each level contributes exactly Cn work, and there are log n levels, giving us Cn log n total work. Therefore, Tn equals On log n. The master theorem provides a shortcut for many divide-and-conquer recurrences. Time to test your asymptotic mastery. These challenges will push your understanding of the subtle distinctions between notations. Remember, big O allows equality, small o requires strict inequality. Theta demands both upper and lower bounds. Omega provides lower bounds, and small omega requires strict lower bounds. Each notation captures a different aspect of growth relationships. Let's see if you can navigate these conceptual waters with precision. This first challenge tests the crucial difference between big O and small o. Bubble sort worst case is that of n squared, which means it's exactly quadratic, both O(n) squared and of n squared. For small o to hold, the limit of Tn n squared would need to approach 0, but since bubble sort is that's n squared, this limit approaches a positive constant, not 0. Therefore, bubble sort is not O(n) squared. It's precisely quadratic, not strictly less than quadratic. This distinction is fundamental to asymptotic analysis. The next challenge explores polynomial relationships. Given f of n equals 5n squared plus 10n, we need to determine which notation applies. The n squared term dominates for large n, so this is clearly O of n squared. It's not O of n because n squared eventually overwhelms any linear function. It's not O of n squared because the limit of 5n squared plus 10n n squared equals 5, not 0. And it's certainly not no-go of n squared because that would mean it grows strictly faster than n squared, which it doesn't. The dominant term analysis makes O(n) squared the correct choice. Here's a fundamental theorem test. If f of n equals theta n log n, what must be true? By definition, theta notation means the function is sandwiched between two multiples of n log n. This requires both an upper bound, f equals O log n, and a lower bound, f equals O of n log n. Theta is the intersection of big O and big omega. You cannot have theta without having both the other bounds. This is why theta provides the tightest possible asymptotic characterization. This challenge highlights the power of small o notation. Binary search is O log n, but the question asks which additional relationship holds. Since log n grows strictly slower than n, the limit of log n equals 0, we have log n equals On. This means binary search is not just bounded above bilinear time, it's strictly faster than linear. Small o captures this strict inequality, showing that binary search fundamentally outperforms linear search for large inputs. Selection sort provides the perfect example of tight bounds. Since it always performs exactly n(n-1)2 comparisons regardless of input, it satisfies both the upper and lower bound requirements for theta notation. It's O(n) squared because it never exceeds quadratic time, and it's Og of n squared because it never does better than quadratic time. This gives us the tightest possible bound, theta n squared. This consistency across all inputs is what makes selection sorts analysis so clean and predictable. This comparison question tests your understanding of strict growth relationships. Merge sort is theta n log n, while insertion sort worst case is theta n squared. The question asks how they relate asymptotically. Since the limit of n log n squared equals log n, which approaches 0, we have n log n equals O(n) squared. This means merge sort is not just O(n) squared, it's strictly faster than quadratic. For sufficiently large inputs, merge sort will always outperform insertion sort's worst case by an ever-widening margin. This loop analysis tests your ability to sum arithmetic series. The outer loop runs from 1 to n, and for each I, the inner loop runs from 1 to I. Total operations equals 1 plus 2, 3 plus n equals n plus 1 with there 2. This is the classic triangular number formula, which equals theta n squared. The linear term n and the constant 1/2 are dominated by the quadratic term. This pattern appears frequently in nested loop algorithms like bubble sort and insertion sort. This question tests your ability to identify incorrect asymptotic relationships. n squared equals O of n cube is true because n grows no faster than n cube. N equals O n cube is true because n grows strictly slower than n cube. N squared equals mo n is true because n squared grows strictly faster than n. But n squared equals O omega means grows at least as fast as, but n grows slower than n cube, not faster. The ratio n squared equals 1n approaches 0, proving n equals n, which contradicts n equal . This exponential comparison reveals subtle differences in exponential growth. Naive Fibonacci is O of 2n, but its tight bound is actually phi n, where phi 1.618 is the golden ratio. Tower of Hanoi is exactly the 2n's. Since phi 2, we have 5n x O, the ratio n2n equals phi r2n approaches 0. This means Fibonacci, despite being exponential, is strictly slower than Hanoi. Both are exponential, but Hanoi grows at the faster exponential rate. This final challenge tests your understanding of algorithms with variable performance. Quicksort's average case is theta n log n, but its worst case is theta n squared. Since best case differs from worst case, we can't characterize quicksort with a single theta bound. Instead, we use O n squared to capture the worst case ceiling and O n log n to capture the best case floor. This combination tells us quicksort will never be slower than O n squared and will never be faster than O n log n. It's the most honest way to describe an algorithm with input-dependent performance. Congratulations! You've mastered the fundamental language of algorithmic analysis. You understand that big O provides upper bounds, big omega provides lower bounds, and theta provides tight bounds. You know that small o and small omega capture strict inequalities through limit analysis. You can analyze iterative algorithms by counting operations and recursive algorithms by solving recurrences. Most importantly, you can prove these relationships rigorously and apply them to real algorithmic problems. These notations aren't just mathematical abstractions. They're practical tools for algorithm selection and system design. When you're processing millions of records, the difference between O of n log n and O n squared isn't academic. It's the difference between seconds and hours of computation time. When you're designing a system that needs to scale, knowing that binary search is O(n) while linear search is theta n guides your choice of data structures and search strategies. This foundation opens doors to advanced algorithmic concepts. You're now ready to tackle amortized analysis, where individual operations might be expensive, but the average cost over many operations is cheap. You can explore approximation algorithms where we trade optimality for tractability. You can dive into complexity classes like P, NP, and P-space, where asymptotic bounds help us understand the fundamental limits of computation. The mathematical precision you've gained here will serve you throughout your career in computer science.